Decide to propose.
You busted the listen.
Welcome everyone. Welcome back to a real Zoom room. That's achievements, small achievements should be always celebrated. There are candies outside in case.
Yes.
So it's an honor to introduce to you Devin Chu. That was deep down in the ILO roots. Went to ILO High School and then he worked with Gemini, I think with Atsuko at the time. With Scott at the time.
Before that, he was at Hilo High working with Scott.
So he's really basically part of the family. Then he moved to UCLA when he got his PhD with undergrads, working on the Galactic Center. And now he's at UCLA, he's a CAC Adaptive Optic Fellow, or with a more complicated name, but the basic is that. And he's now will introduce to us a talk about the Milky Way Galactic Center, a laboratory for extreme astrophysics revealed with AO. Thank you, everyone.
Thank you. It is such an honor to be back. It's just being able to wander through the halls again. It makes you feel so familiar and so nice. Great to see familiar faces again. It's just such an honor and pleasure to be here. And even familiar faces that I didn't expect to be here. For instance, like Cicero, I believe I was your TA for my first year of grad school. Astronomy is a small community. Yeah. So anyway, but the point being, it's such a pleasure to be here. And it's an honor to talk about the work that I've been doing with my collaboration. And we'll be going over a little bit of review. So hopefully you'll be able to find that enjoyable. But first I'll begin by talking a little bit about my roots, as mentioned a little bit here. So I just want to take a few moments to talk about a little bit about me and get the context of who I am. This here, my building might look familiar to some of you in town. This is where my interest began, at the Hilo Public Library. I went with my mom, we checked out this book, Our Solar System by Seymour Simon. I saw the cool images of the planets. And basically from that point, I knew that I was really interested in astronomy and I wanted to pursue that potentially as a career. And so I was really fortunate, and I want to say big mahalo to Gemini for really playing a huge role in nurturing my scientific interest. So it's one thing to become interested in astronomy, and it's another thing to then carry that interest forward. And so through Gemini, they really played a huge role in that. Through programs such as Journey Through the Universe, I was able to be exposed to different scientists and different demos that got me further interested and kept me going. And then as alluded to earlier, my first connection directly with Gemini was with Peter. I worked on a light pollution project while I was at Hilo Intermediate School. Through Peter, I was able to essentially check out a Department of Education telescope and got to take that around the island and do some little light pollution experiments. And I thought that was really cool, and that just kept me going. As we just talked a little bit briefly here, I got to do some science fair projects with Scott. I was working on stellar classification. Little did I know that this became very relevant for what I kept doing further on all the way through grad school. Again, and I also got to come back as an undergraduate, as an Akamai intern, working with Atsuko and Scott again on white dwarf astroseismology. And again, at the time, I didn't realize that I would be doing some periodic temporal sampling analysis, which again carried over all the way to grad school, but I thought that was kind of funny too. And I also forgot to mention through Scott on my first project, learning SQL language, which I use today too. I just never thought I would have carried all the way through, but it's funny how it works. So one of the things I want to say is, while growing up in Hilo, I wasn't really aware of some of the really cool science that was happening just up the mountain growing up here, and particularly being done by the UCLA Galactic Center group. So every summer, the UCLA Galactic Center group would point telescopes, sometimes multiple telescopes, at the same region of the sky every summer and look at this very interesting and intriguing region. So this is a really cool photo here showing 4 lasers pointing at the Galactic Center, including Gemini's, and the Gemini's off screen here. But it's just one of the things that was cool scientific developments that was happening right at the mountain that I really wasn't as familiar with at the time. So I thought that was really cool. And now fast forward to today, here I am with the UCLA Galactic Center group, and I just think it's been a really cool opportunity to really realize that I'm back here now as an astronomer, being able to do my own scientific research with the collaboration here gives me an opportunity to come back home when we do observing. And it's just really a very surreal experience. And so the work that I'll be presenting today, I really want to emphasize that it is really presenting on behalf of our collaboration. And a lot of the science that I've done that I've either led or whatnot, it really wouldn't be possible without everyone's input and knowledge. So I've really been able to benefit from that. Okay, so before we get started, I do want to poll the audience a little bit. I guess it's also relevant for those on Zoom as well. And so when one hears the galactic center, like what scale do you think of? So I have a couple of options here. What so just polling the audience, what do people think of? Like option 1, 2, 3, or 4? Like what scale? I'm just kind of curious here. 3, okay, we got a central parsec. Yeah, central parsec. Okay, even kiloparsec is good enough for. Yeah, it's funny. It's a funny.
I don't even know.
Yeah, right.
It's like, is it this big? Yeah, okay.
Yeah, what's funny is I think even at least we have these like very dedicated galactic center conferences, and you get the same thing. People are like, well, central kiloparsec, that's pretty close enough, right? That's all I'm really interested in. So I think it's like a funny question to ask. Similar to, I think when people say, right, what do you think of when you think of high redshift, right? What redshift are you thinking? People say 7. Someone's like, oh, if this 3, that's good enough for me. So for me, I'll be talking more about the central 0.01 parsecs. And so this is what I currently think of. And so my talk will really focus on within the central 0.04 parsecs. We're really getting deep in there. But again, I also, from this point, I also want to emphasize that I'll be focused on this region, but there's a lot that's happening even a parsec out that in some ways I feel like I still have to remember and think about and refresh my memory. But so when I say galactic center, this is the scale that I'll be focusing on here. Okay, so first off, I want to introducing the region again here. This is the galactic center infrared light. The scale bar here is about a small part, about 30 parsecs. So with this image, we're looking at really a scale of hundreds of parsecs. So again, this is beyond the scale that I'm used to. But the main thing I want to point out here is that we just see that the incredible stellar density of this region, and also how, not only is very dense, but you can also see a lot of dust patches and whatnot. And the main thing I want to say with this is, if we want to look at the galactic center, particularly the very core, we have to look at infrared light. Visible light is extincted by about 30 magnitudes, so there's really not much we can do in that particular science field. But when we go to infrared, the extinction drops down to maybe about order of 3 magnitudes. So that allows us to really, it makes it incredibly crucial for us to look in infrared if we want to study stars so close to galactic core here. But again, like I said, I'm not interested in this large. This is, for me, it's very, very large scale. Let's go ahead and zoom on into the very center here. So now we're dealing with, again, like 6 arc seconds, or about a quarter of a parsec here. So now, though, again, to really stress this region here, again, being so crowded, if we don't, just the incredibly high dense nature of stars, even when we have, like I say, a 10-meter class telescope, we really can't, it's hard to resolve individual objects, especially if we're looking at this box region here, which, spoiler alert, is where like the very center of our galaxy is. But again, if you look here, we just can't resolve anything individually. So in order to get past that, we really need to use adaptive optics. And I just want to stress here that adaptive optics is incredibly crucial for us to be able to look at individual sources. So really, without that, we won't be able to resolve individual objects and then to perform some of the science that I'll be displaying here. So again, just these main 2 points. If we want to look at the very center of our galaxy, we need infrared wavelength coverage, and we need adaptive optics. And what's great is Gemini is great at both of those things. So I think Gemini is very, very fitting to be able to look at this region. So again, we're going to take, here's another image here of the galactic center at 2.2 microns, taken with adaptive optics. This is taken with the Keck NERC2 infrared camera. So again, this is the very center of our galaxy, really represents the only place where we can resolve individual stars in a galactic nuclear star cluster, which makes this region very interesting. But again, like I said at the beginning of this talk, I'm really interested in the very center of this region. Again, on the scale of like very, not even a parsec here. So let's go ahead and zoom in again here. And so this here is a video, I think it should play now. This here is a video of our imaging data that we've taken over the course of 25 years. What's really cool is we can see, for one thing, the difference that adaptive optics makes. So this is where adaptive optics begins. And what's really cool is that we can really see these fast moving stars over the course of like 25 years. These are what we call these stars the S stars, and this video highlights the brightest of these fast stars called SO2, and it's traced its orbit around an infrared source known as Sagittarius A star. I guess it's also in the radio, very bright in the radio as well. This here is another animation showing tracing the path of these galactic center S stars as well. So as we trace these motions of these stars, we can see that they all orbit around this central point here that doesn't seem to be emitting a lot of its own light. And through the motion of these stars, we're actually able to prove the existence of a supermassive black hole at the center of our galaxy. And again, looking at the scale here, where these stars are like really, really close, we're again dealing with not even arcsec, really a tenth of an arcsecond, or in physical units about 0.004 parsecs. So we're really zooming in here to the very center of our galaxy.
Are the different colors for masses or brightness?
Oh, great question. Sorry, I'm going to play it. So I guess the colors are just different orbits or just for different objects. But maybe one thing I'll point out here is as the line becomes solid, that's where we begin to have spectroscopy of these objects. And I'll talk a little bit more about that on the next few slides, but that's a great question. So as I mentioned again, the orbits of these S stars have confirmed the existence of a supermassive black hole at the center of our galaxy, with about a mass of 4 million solar masses and about a distance of 8 kiloparsecs. And so this is one of the really cool, exciting works that we could get from monitoring these stellar orbits. And then one thing I also want to stress too is that these S stars, they really represent a stellar population that can probe the dynamics of a very extreme environment right next to a supermassive black hole, which makes them interesting in that regard. So the next point I really want to bring about here is how adaptive optic spectroscopy of the galactic stars really led to another big leap of our scientific progress. So as one can imagine, without adaptive optics and the light's all smeared out, there's no way we could do spectroscopy in these individual sources. But once we had that, it allows us to really do spectroscopy and then learn a lot more. So one point I really want to bring up here is this really puzzling stellar population here. So when we took spectroscopy of these stars, these S stars, what's really interesting is we revealed most of these to be main sequence B stars. So here's an example spectrum of the star SO2. Really the only main lines that we see are really strong hydrogen absorption line and some helium lines. Again, this brings me back to my days of working with Scott and stellar classification. And just some properties here for some B stars are very, very hot, very massive, and very young, with some properties listed on that first bullet point. But the interesting thing to say about these stars is that young stars aren't expected to form so close to supermassive black hole, because when they're that close to the central black hole, you'll get these tidal shearing effects where a gas cloud cannot collapse into form stars. And again, these stars don't live very long, so they can't be formed outside and then make their way in. So the fact that we find them so close to supermassive black hole is really interesting. It's something that wasn't expected, and it's one thing that Professor Andrea Guez coined the paradox of youth. Why do we find such young stars so close? Fast forward in really a few decades, as we're able to play this game of keep watching these stars and monitoring them spectroscopically, getting a really nice orbital model, we can then actually play the game of, well, does Einstein's theory of general relativity hold up? And it turns out, yeah, it does. And we were able to do this by monitoring the star SO2. So in 2018, SO2 passed closest to the supermassive black hole once again. And as we got to use that year to really monitor its rate of velocity very closely and see if it deviated from a Newtonian orbital model, which it did. So this figure on the right here, the x-axis is time, and the y-axis is basically the deviation from a Newtonian model. And what's really cool is you can see a definite deviation that seems to agree pretty well with what general relativity predicts. So what's pretty cool is, again, we can play this game of not just monitor orbits, but really test fundamental physics. Does general relativity hold up so close to a supermassive black hole, and which it should, and so far it seems to be like that. It is. And I also want to stress as well that this result here includes Gemini and NIFS data that was very helpful Yeah, anytime just let's get more data, but also into the weeds, so we can do a lot more systematic checks. It's just a good way to good sanity check. So anyway, it was like really helpful. I don't know, for those that remember, 2018 was actually a very challenging observational year. We had the volcanic eruption and the earthquake associated with that. The weather was pretty bad for us. So any data we got was very helpful. So we're really grateful for NIFS that came out to be very useful. Related to general relativity, the next thing we're also really interested in is looking for the precession of the periapse of SO2. So similar to how Mercury precesses around the sun, SO2 will do that as well around the supermassive black hole. And so in fact, it's already been reported by the gravity collaboration in 2020, and we're stay tuned for our result. We're still going through our data set here. And so even though this is mostly a astrometric result, I do want to stress that the getting the orbital model is very important for this type of result. And so that's where the rate of velocity still come in for that. So again, we use NIFS for the relativistic redshift. And so NIFS will also be very handy for the for this result as well with the orbital model. And another cool thing I want to stress as well, that or a really cool fundamental physics test that we can do with spectroscopy is like testing things like the fine structure constant. So one of the cool things that we've been able to do as well is like look and see, are some of physics constants really constant, or do they actually vary in the gravitational potential? So this work by Orley and Hees in 2020 looked at the spectral absorption lines variations in different stars of the galactic center, and we're able to place a variation constraint on alpha, the fine structure constant, to about 10 to the minus 6. And while it's not as stringent as some other works done on white dwarfs or quasars, the main point I want to state here is that the study is unique in that it really, the depth of the gravitational potential that we're probing is very extreme compared to other examples, and also the compactness of the central source. And again, NIFS played a very important role with this. What's great about NIFS is the wide wavelength coverage allows us to get multiple absorption lines. So again, that NIFS is very necessary for this work. Okay, so those are just a couple examples I just wanted to highlight of really how spectroscopy and the adaptive optics was important for this work, and some of the really cool science that came out of it, and also how NIFS has played a role. But now for like some of the work I'll be talking about here is more about some of my individual projects that I've been working on. And so for that, let's go ahead and return back to these puzzling young massive S-stars that are around the black hole. So again, just to bring it back again, it's really interesting that we found these the young main sequence B stars so close to the supermassive black hole. So one of the questions we're just interested in as well, okay, so they're there, are they similar to other main sequence B stars that we see around the galaxy? And in some ways, one question we're kind of curious about is, are they also in binary star systems? So this is a little quick review here. In the solar neighborhood, most of these massive B stars, they come in pairs for the most part. And so in fact, some work by, for example, Sana et al. 2012, these OB stars can be as high, have a binary fraction as high as 70%. So then one of the questions we're interested in is, okay, are these S stars, do they also have a similarly high binary fraction? If they're similar to like the solar neighborhood, then they should be. Or does the environment of the galactic center affect this particular trait of the binary fraction? So we'll see. That's one thing we're interested in. Okay, so just for a quick review, there's a couple of main ways that we can look for binary stars at the galactic center. So we can use, for instance, the eclipsing method using imaging.
Oh, is it that?
I thought maybe you were playing the sound from the.
Oh yeah.
That's what they sound like as the eclipse.
Yeah, exactly. All right.
Did you really do it, or was it coincidental?
I did.
Thanks.
That's the
So quick review. Yeah, so we can use look for binary stars using the eclipsing method. One of the pros is that because you can use this imaging data, it's definitely a lot less expensive compared to spectroscopy. But one con is that we essentially it's a lot less sensitive to different orientations, binary orientations. So what is cool about using the rate of velocity method for those that are familiar with planets, a lot of the same benefits come with that, and that we're a lot more sensitive to different orientations compared to the eclipsing method. And we can also get things like stellar masses and other traits. But the con is that it is very expensive for telescope time. Spectroscopy just takes a lot of time to get all those photons that we need, and then also to propose for multiple epochs. It's very expensive. So that is just one of the cons, but it does provide a lot of benefits. So what's been, actually, I'll come back to this point here. And so I should say that there has been an interest, of course, in looking for binary stars so close to supermassive black hole, both with photometry and spectroscopy. And so, for instance, there is evidence seems to show that when we look at the population as a whole of these stars, the eclipsing binary fraction seems to be consistent with that of the solar neighborhood, but done by these works shown here. And but the work in the spectroscopic side of the binary search is a little more limited, at least going back to like 2014, where again, because of the challenges of spectroscopy and the expensive nature, they really only focused on the very brightest stars of the galactic center, and they actually didn't include the galactic center S stars that were found, that I'll be focusing on here. So before 2014, there was no spectroscopic search for spectroscopic binaries among the S stars. And so for this work, there didn't seem to be any signs of photometric binary candidates, but these S stars are also excluded from spectroscopic sources. So there was definitely an interesting gap in our knowledge that we wanted to try and probe here. So another reason why we're really interested in looking for binary star systems is that they may explain why these S stars exist, where they are around the supermassive black hole. And I'll go over a few evolutionary mechanisms here. So one potential thought is that these S stars could be, in fact, former binary stars where one is captured by the supermassive black hole, tidally disrupted. It remains as the S star we see today, and another part of it is then ejected as hypervelocity stars, which we see around the galaxy. Another thought is perhaps these could in fact be merged stars. So perhaps you could have older stars that are closer to the supermassive black hole that actually merge. When you have a supermassive black hole, the three body interactions definitely encourages merging. So that could be, and then what we see is a merger probably looks sort of like a main sequence B star. So that could be what they are instead. Or potentially if these S stars are in fact truly binary star systems, perhaps they were scattered in as whole binary star systems. So that's another potential theoretical thought that, what these S stars could be. So then, well, we want to be able to potentially distinguish between these evolutionary mechanisms. So how can we go ahead and do that? Well, we can actually use the observed binary fraction to then attest to how these particular evolutionary mechanisms may, these particular mechanisms. So we look at it from a term of a binary fraction sense. If we think that these stars are actually all disrupted binary star systems, then we would expect the binary fraction to basically be zero, because they all were binary systems and now they're not. They're just single stars that just remain as they are, or that have remained and their companion has been ejected off. On the other flip side, if let's say they do match the solar neighborhood population, which they seem to be suggesting from previous works, and they're just scattered in, then they should have a binary fraction that should be around 70% or pretty high. And then in the middle, you have this where like perhaps you have binary stars that have then since merged. You would expect more of a expected binary fraction a little bit between the two, essentially. So that's just one of the ways we can distinguish between these mechanisms in a binary fraction sense. So coming back to this again, the data side of this experiment is that what's been really nice is there's now the data to then now look for these stars, binary stars using spectroscopy. So again, we've been using over a decade of spectroscopic data. Like I think we were told it comes up to like almost 50 full nights of data with primarily Keck Osiris, but we also again have some NIST spectroscopy here. So now we actually can start to have a data set to really start probing and looking for spectroscopic binary systems in spectroscopy. And what's also exciting too is especially in the more recent years, we have multiple epochs per year. And this is now allowing us to increase our sensitivity to spectroscopic binaries. And a lot of this comes from the drive to look for some of these other general relativistic effects where we really needed to get a lot of sampling for our orbits. Well, so one of the nice product of that is we can also, it gives us more sensitivity to shorter periods because now we have a lot more data to then look for shorter period binaries as well. So I am fast forwarding a little bit here through a lot of the methodology, but essentially I'll, for those that are interested in a lot of the details of how it's done, it's in this paper of Chu et al. 2023. But to go over maybe some of the main interesting result here is that going through all this data and doing a lot of periodic analysis, we actually didn't detect any signs of binary stars in our sample. And using our lack of detections and a bunch of simulations from that to our sensitivities, we're actually able to place an upper limit on this binary star fraction of the S stars. So we're able to place a 95% confidence limit on the S star binary fraction at 47%, which is basically this point here. So this figure here, just the main way to look at it is, I would say, is for this binary fraction on the y-axis, the x-axis is essentially the confidence limit. So, but the main thing to take it from it is we can place this 95% limit at 47% binary fraction. And then coming back to how can we connect this to like what we know about the solar neighborhood is that we can exclude pretty confidently a very high binary star fraction of 70%. And it seems to be that these S star binary fraction is inconsistent with the massive star binary fraction in our solar neighborhood. And so just to kind of stress this again, if we think that the binary fraction, or it seems that, so coming back to the evolutionary mechanism, it seems that we can now exclude pretty confidently that in fact, these are whole binary star systems that are just scattered inward, because again, we would expect a higher binary fraction potentially that of like 70%, but yeah, we're able to place an upper limit at 47%, which I think pretty well disfavors this particular mechanism here. So another interesting that we're interested in too, or I should say connecting back to the other models, it does seem to be consistent with a binary merger model for stars closest to the supermassive black hole. So just really talking a little bit how this works is as you get binary stars closer to the supermassive black hole, three-body interactions with the supermassive black hole and the binary star system causes them to merge. So essentially, as you get closer in, more binary stars have most likely merged. That's what this figure here is showing. So the x-axis here is essentially the distance from the supermassive black hole going further out to the right. And then fraction of binary stars is the y-axis. So essentially what it's saying here is as you go closer to the supermassive black hole, so going to the left, your population of simulated binary stars goes down. And so one of the exciting things is we're actually able to, it sounds like our result of about 47% seems to be pretty consistent with this merger model, which is pretty cool. And so, so based on how the binary fraction limit that we're getting, it seems to be consistent with these particular the capture mechanism and injection mechanism and the merger mechanism. So again, like, well, we're not able to exclude a 0% fraction, but it does seem to be pretty low. So that seems to be consistent. And as I said earlier, it is consistent with this expected binary fraction from a merger model. Okay, so that describes some of this like interesting work that I was working on with looking for binary stars at the Galactic Center. But I do want to talk about a little bit now about how some really cool upgrades and adaptive optics will really play a big role in further progress in science at the Galactic Center. So one of the cool things that I've been working on as a postdoc is thinking about how upgrades to adaptive optics can help out with our observations at the Galactic Center. And so one of the very cool points here is that the Galactic Center is a very great candidate or target for looking or for using an infrared bright tip tilt star. So here on the right, this figure is actually taken with Gemini, showing kind of like the layout of how things work here. So, so one of the exciting things again is, for the most part, in the early days of adaptive optics, we have to use an optical tip tilt star to do our corrections. But again, dealing with the Galactic Center, it's a lot of extinction visible, but we have some very bright infrared stars. And so what's exciting is there's this really bright star here. It's called IRS-7, which is very bright in the infrared, and it's only 8 arc seconds away from where we're interested in, where we usually put our laser. Whereas the optical tiptoe star is about 20 arc seconds away. So if we're able to take advantage of this infrared tiptoe star, it really can cut down on some of the tiptoe error that we deal with on our observations. And so I think that's really cool is this, this Gemini image really shows this scale that we're working with here. And so what's really exciting is that the infrared tiptoe star and using the infrared tiptoe sensor, it really improves our adaptive optics correction and improves our galactic center data quality. So this figure here on the right just shows an example of an Keck Osiris data cube. And now this is the same field. They're actually taken on the same night. On the left, we're using the infrared tiptoe star and sensor. And on the right, we're using the optical tiptoe star and sensor. It just so happened that night we had to like switch between the two. But what's really cool is that you can see the very the visual difference already, what the infrared tiptoe star makes. And so in this SPIE proceeding that I was able to put out, what's really neat is we're actually able to get a lot of benefits. So in imaging, we get an improved Strel and full width half max. And then in spectroscopy, we get improved spectral signal, since we can concentrate most of our photons together. And we get improved full width half max, especially if we're using imaging spectroscopy. And so what's really exciting is that if we can use this infrared tiptoe star, we'll get a lot of scientific benefits just from that alone. So we can get, again, more precise data for our stellar orbits. In the case of looking for binary stars, will be more sensitive to radial velocity variations and et cetera. So that's one of the very exciting things about that. And it sounds like especially for adaptive optics, for the ELTs, infrared tiptoe star sensing will be very crucial for that, especially for the science that these ELTs want to do. So the Galactic Center is a great case for that. So if you're interested in some of these more quantitative results, they're in this proceeding, and there'll be a paper that's being put together by a grad student in the group as well. And finally, I also want to talk about here is once we're able to update the the adaptive optics system, if we can then put some next generation instrumentation just behind that adaptive optics systems, we'll be able to get a lot of really cool and improved sensitivity, and then this will lead to another leap in science. So this simulation here was done by Tuan Do at UCLA. The left here just is showing current Keck AO capabilities. If we're able to then do this next generation AO, which is going to incorporate the infrared tiptoe star, some multi-conjugate AO, we can get probed down to further sensitivities. The right is what we hope to get with ELTs. But even with this just next generation, what'll be nice is we'll be able to, for instance, push down our spectral typing limit down by a few magnitudes. So right now there's a lot of stars that we don't know if they're main sequence stars, if they're late type giants, just because they're too faint. We can't get enough we can't get spectroscopy of those stars, but we'll be able to probe further limits down with next generation AO. And we'll also be able to find deeper stars or fainter stars in imaging, which presumably are closer to the supermassive black hole at shorter periods. This will allow us to, again, probe stars closer to the supermassive black hole with shorter periods. Maybe we'll be more sensitive to things such as the precession of these stars. And as we build up a sample of stars that are closer to the supermassive black hole, we'll be able to do things like test the spin of the black hole, because you need multiple orbits for that work. We can then also test things such as the extended mass of the black hole. Like right now, for like modeling purposes, we consider the supermassive black hole a single point source. But if we assume that there's stellar remnants or other essentially dark mass that could be around the black hole, that actually would affect the way these stars precess. So this allows us to become a lot more sensitive to those type of experiments, which is really exciting. So I'll leave here some of my conclusions. So just want to say again that the Milky Way Galactic Center is an ideal laboratory to test like fundamental physics and astrophysics in extreme dynamical environment near a supermassive black hole. The infrared wavelengths and adaptive optics are very crucial for this work due to the stellar crowding and the dust extinction. And so just present a little bit of some of my work here looking for binary stars at the Galactic Center, and it seems like closest to the supermassive black hole, there seems to be a little bit of a dearth of binary stars, which is interesting. And finally, I want to say again that upgrades to adaptive optics will lead to further improvements in galactic center science. So with that, I just want to say mahalo nui loa. Thank you so much for listening. And thank you very much. Any questions?
All right, so I have, so if you think these are B stars, I'm assuming in the galactic center, so that they're going to peak in the UV or, a lot hotter. With 30 mags of extinction though, is there anything you can do, or have you guys been thinking about any sort of like small scale, like SAT UV missions where you can like look at these things in the UV and see if, I don't know.
Yeah, that's a good question. I mean, I think there's just so much extinction, you can't get anything. So the unfortunate thing about the wavelengths that we're working is I'm glad we can get some lines, but we're pretty limited to what we can get. With JWST, we could potentially get some further lines, which I think will help with that. I haven't worked too much with the JWST data, but we've gotten some. That's another whole interesting challenge. But JWST will definitely help with spectral typing as well. But yeah, the biggest thing is we're just limited with just the lines we see in the infrared. So that's definitely the challenge. What is nice is at least I feel like a big part of the spectral typing is if they're giants, the CO band heads are very obvious. So that's good. But finding the B stars is a little bit harder because sometimes that bracket gamma line is all we have and it can be kind of noisy. So it's definitely a challenge. I mean, it'd be nice if we could just pierce a hole through it. Not have to only use infrared, but that's what we can do.
Oh, sorry. Very nice talk. Thank you very much. I was just wondering, how would you go about proving this ejection or merging mechanism? Is it looking for like hypervelocity stars or those types of? Yeah. So distinguishing between the two, I think that's a good question. I think, the subtleties for all the different these mechanisms, there's definitely a lot of like little details. So I think to distinguishing the two, potentially if we could push that binary fraction even lower, that would be a way to do it. I think one thing I didn't get quite a chance to talk about it, but what is interesting is at the galactic center we do seem to see products that could be merger products. So there seem to be these gaseous features. So that seems to also be in favor of the merger mechanism. I know what's interesting about the hypervelocity star method. I think one of the challenges is always tracing back current hypervelocity stars back to the GC. So that's, I think, a challenge, but I think there's a lot of work in that. So yeah, to go between distinguishing the two, that's my kind of inkling of how you would distinguish two. But I also don't think there's reason to say it is one or the other. It could be both as well. So yeah, I don't know how satisfactory answer that is, but Fair enough.
yeah.
Thanks.
Can I just quickly follow up with this? Yeah, so following all up with that. So you've got this 20, 30-year baseline. Do you see changes in like the brightness of the stars that would indicate maybe the merger or an eruption or something dynamical had happened in the stars themselves?
Yeah, great question. So I haven't done as much with the photometry data, but there's definitely a lot that's gone in there. So one of my colleagues, Gautam, he does a lot of the photometry work. So he's found some interesting like binary candidates or stars. So there are definitely some interesting variable sources as well. But I think one of the challenges he finds in photometry is a lot of stars are kind of variable, and that can go from like dust screens passing in front and whatnot. But yeah, he does a lot of like really interesting work on that. So I would defer to some of his works. But yeah, there's a whole another data set in photometry, which is really interesting. Monica?
Great talk, Devin. I have a question about this, the plot you showed earlier, binary fraction versus the distance from the black hole. I was wondering if that, this one. Does this depend on the mass of the black hole?
I believe the simulation does. So this simulation that was done by Stefan, he's assuming this Sagittarius star mass. I think and this is where I'm trying to remember. I believe it should depend on the mass of the supermassive black hole, because that would affect the strength of the Kozai leadoff mechanism, I should say. I mean, even Sister might be more qualified to answer that, but I believe that the black hole mass should play a role in that.
Yeah, that's very interesting. So in a way, this could be like a methodology to search for. Yeah, I'm just throwing it here, like intermediate mass black holes or.
Yeah, I presume. Yeah, there probably is a scaling. Like, yeah, if you scale the blast of the black hole, it probably would affect the scale. Yeah, that's interesting. Quite. Yeah, I can't speak to it much more detailed than that, but yeah, I think. Yeah, I think it should depend on the mass.
Thanks.
I have a question. That is a really good question. How did you went about to calculate probability? Do you like select a volume based, like a volume window sample and get like integrated like fraction?
Yeah, good question. So yeah, again, I did skip over a lot of this methodology, but the big thing I did is I essentially simulated lots of essentially mock binaries, rate of velocity curves, and then saw using our data and our sensitivities, look to see how sensitive we are to these simulated binary populations. So I drew from essentially a Sana generated population, created a bunch of rate of velocity curves from that, and then went to see if we would be sensitive to drawing from those populations. And that's how I came across our limit. But yeah, so it's more of essentially a population synthesis, creating a synthesized rate of velocities, binary rate of velocities.
Mazen, you want to speak up?
Yeah, that was a really good talk. Thanks. I was just curious, so is this Keck plus NGAO system, is this a planned upgrade?
Yes, so this is, well, this simulation was made, I think, before, I can't remember how much of it was planned, but the idea is like this should be part of this Kappa upgrade, which is the Keck. Yeah.
Okay,
yeah.
so this is, okay, and this also uses that tip tilt, the infrared tip tilt sensor?
That's a good question. I mean, so right now Kappa plans to use the infrared tip tilt sensor. When the simulation was made by Tuan, I'll have to ask him if he assumed, I believe it should incorporate it. I believe it had the infrared tip tilt star or tip tilt sensor built into the simulation, or that sensitivity built in, but I'm not totally sure, but I believe so. I believe that was built into the sensitivity.
Okay, but this is basically Kappa. Oh,
Yeah,
that's all. Right. Okay, thanks.
Yeah, that's my understanding when the simulation was made. It was assuming the Kappa sensitivities.
Thanks.
Michael?
Hi, Devin. Great talk. I was curious to hear more about your thoughts on Kappa plus Liger versus JWST. Like, where do you see kind of the two instruments or two platforms complementing or competing, or what do you think?
Yeah, great question. So with Kappa and Liger, which is a planned instrument at Keck, essentially it's almost like Osiris, like an upgrade on Osiris, and it uses the Iris technology onto an instrument essentially. So what's great with Liger is that we'll be able to get the spatial resolution that we can't get with JWST. So that'll be really helpful, especially for if we want to do things like the fine structure constant experiments or individual RV variations of the star's closest supermassive black hole. That is where Liger will really play the biggest, I guess, compared to JWST. Liger will be really helpful for that because we'll be able to really resolve these individual stars better and then and assign their velocities to those. With JWST, I think the benefit from there comes from being able to spectral type stars at I think a wider, I can't remember now the field of view, but they'll be helpful for spectral typing stars. I think will be further out where it's not quite as crowded. So I think that's how they'll be able to complement each other. Because what's nice is if we can get the rate of velocities from Liger and maybe better spectral typing from JWST, that'll really help with some of these bigger stellar population works, which I didn't really get a chance to talk about in this talk, about like exactly where are these young stars distributed, and then because it could ask a lot of interesting stellar dynamics from that, and also stellar population and stellar evolution from where they're distributed. That's a good question, Mike. I think, yeah, that's how I would go about that. I think, yeah, the strength of the two instruments or telescopes I think they do complement each other in that regard.
No. Got the answer. Thanks.
Ryan?
Yeah, hey Devin. Thanks for the nice talk. I had a question about your bullet point 3 here about the
Yes.
binary fraction.
Mhm.
So you're saying that it's inconsistent with that Sana result that over 70% are binaries. Is it that, are you also able to constrain that they didn't actually form initially as binaries, or that they could have, like maybe over 70% of them did form as binaries, but there's some kind of interaction with the black hole that ejects them or causes them to merge? Is that the results? Is it that they probably were initially formed as binaries, but it's the influence of the black hole that caused them to not exhibit the same fraction?
Yeah, that's a good question. I know I'm trying to think of maybe a way of seeing. I would say this work maybe is not quite as sensitive to like the pure formation mechanism that could have brought all these B stars so close and like that binary fraction, but at least maybe to be the most like conservative, just at least it doesn't seem to match that of Sana. And I think I would say I would attribute that more to like potentially the physical dynamics of the supermassive black hole. But yeah, as far as the full like formation of these B stars, I don't know how sensitive this work is to that particular mechanism, like how a gas cloud collapse and those type of elements. Yeah, but that's a good question. So I think I would lean more toward it's more speaking to the physical dynamical effects. Yeah, but I don't know if that can speak to how the initial, like say the initial binary fraction that I don't think I could constrain from this.
Okay, sounds good. And then just to clarify, so the young stars that you looked at, those are primarily like the S stars, or did you look at the entire like central cluster?
Oh yeah, good question. So it's what I'm talking about here is the S stars and the particularly young stars, but in this field of view, there are also old stars as well that I include in the analysis. Essentially, I can't really constrain those because essentially like their variations would be like really, really small. So I don't really talk about that result here, but it is in the paper. And then this does focus closest in again within like an arc second of the black hole, because beyond that, our radial velocity coverage essentially drops off like completely. We might just have 1 or 2 data points and that's it.
Cool, thanks.
Devin, I'm wondering if you wanted to push your detection limit down to say 25% of binary fraction, what's your limiting factor? Do you need higher strail? Do you need more time-based? Do you need more photons?
Yeah, that's a good question. So I was thinking about this, and I think the time baseline helps. But then it's a good question. There's a multiple factor. I think the time baseline would help. But also the detection, being able to push that limit down as well. The managed detection would be helpful too. But at the same time, we'd also then need multiple epochs of that improved detection. So my inkling would be those 2 elements first. I mean, improved rate of velocity precision, I mean, will help, but I think the bigger improvements come from the longer baseline and the improved sensitivities. Yeah.
I was wondering, now that we have the image from the black hole from the Event Horizon Telescope, we have like more indication. You know that the thing is spinning somehow. You know that you have some measurement of the mass. What you're learning if you remove these as free parameters on your stellar motion. So now you put the mass as like known things, and then can you improve your like orbital motion? You can improve the precession estimates from that.
Yeah, good question. So what's nice is pretty much from our orbits, we like essentially we can keep all those parameters free and we get a pretty good model. Yeah, as far as this, using the spin, yeah, that would be interesting. Yeah, I'm not quite as familiar with how like the spin, like having the spin from the EHT would affect the precession. But yeah, that's an interesting question. Yeah, but pretty much for the most part, yeah, we were just able to use what we have, our data, to get the models. But yeah, that's something I don't think we've tried, but it would be Yeah, interesting. Yeah.
Any other question? If not, we can thank our speakers again. And for people here, if you are interested at lunch with Dave in the Manali, you're more than welcome to join us.
Yes, and